tension is that on the one hand, you want to embrace and explore all these different areas. But on the other hand, if you're going to end up doing collaborative, interdisciplinary research, you're going to need to bring something to the table that you know better than anybody else. So I think you also need to think about that and not allow the search for breadth to leave you in a position where there's nothing that you really know well enough that you can be the expert in that area.
I don't agree entirely. So my daughter is a freshman in college, and she called me one morning this summer. She was in California and I was in Paris. So it was 4 a.m. in Paris. And she said, "Dad, I figured out what I want to do with my life." And I thought, oh my God, she's going to be a freshman in college and she's figured out what she wants to do with her life. This is awful. But I said, that's important. Tell me what it is. And she said to me, what she wants to do is not that important. But she says, "Dad, I'm going to cure autism." I thought to myself, well, that's great. And that was the end of the conversation. 5 minutes later, she called me back and she said, someone who's about to be a freshman in college, does that mean I have to do an MD and a PhD? And this is when I thought to myself, no, this is terrific, because when I grew up and became a neuroscientist, I didn't know I wanted to be a neuroscientist. I didn't have the opportunity to learn all the different disciplines that go into being successful in this field these days. Whereas what I could tell her was, you need to take physics and math and genetics and biochemistry and cell biology. You need to become a generalist so that you have at your disposal the language and the tools. I think there's a real tendency to specialize too early. And I encourage you to develop a broad background and worry about specializing later. Thank you.
Okay, I would like to start out with a comment, and I would like to hear your opinions on this. Firstly, we heard Brian's talk, and he had mentioned that the brain has the inverse problem. We have a 3D world, and we have 2D vision. And relating that to Christopher's talk, it seems like the world is so infinite, and what we have is finite. And in order to process the information in a very coherent manner, we have the cognitive limitations imposed on us, and I would like to hear, and that's what makes us be normal. And I would like to hear your opinions on that, and I have another question. Should I carry on with the other question, or
let's go ahead and let that question be addressed. We'll give you a chance to ask the second part.
One thing to say about these limitations that have been discussed is there are at least two sort of main threads of interpretation of a lot of these results in the field. One is to trumpet them as limitations and to talk about how fantastically irrational we are. The other perspective to take is to look at these limitations as the reflections of amazingly efficient heuristic processing. You can get the right answer, but in many real-world situations, one has to deal with time constraints, deal with memory constraints, and this sort of thing. So I think that our minds have been tuned through quite a long evolutionary history to respond to certain types of information in certain ways. What cognitive science can help us do is to help identify those situations in which our minds are well-tuned to operate and those in which they're not. I'll give you a very quick, specific example. We heard from Chris about base rate neglect. Well, it turns out that if you're reasoning about percentages, then almost everyone commits base rate neglect and makes all sorts of errors. If you rephrase those problems to yourself, not in terms of percentages, but in terms of frequencies, so instead of thinking about, say, 65% of people, you think of 65 out of 100 people, these errors drop precipitously, and suddenly we're able to reason about this. And there are some interesting thoughts about how that could be explained by the fact that we didn't encounter percentages in the environment in which we evolved, but we encountered frequencies. That particular example illustrates the point that we have these limitations, but learning about them can help us identify when we're in situations where we should, say, trust our instincts, and when we're in situations where we should be a little careful about them. Does that at all address your question?
You want to go ahead and follow up with your part two?
Okay, part two is quite unrelated. It's more on, I come from a computer science background myself, so I would like to hear from the viewpoints of computer scientists. What I notice is I do computational modeling in neuroscience, and what I notice is that the main thing is the information is too defragmented. The kind of modeling that gets done is at different levels all around the place, and people just pick up a part of the problem and work on it, and there is no consensus on which level of modeling to be used, what to do, and different models just come up out of the blue. Do you think that in the future, this information that we have right now and working on computational models can be integrated in some way to have some basic principles and everybody working on similar principles and have it be a more collaborative effort than a defragmented one?
I don't know the answer to your question, but let me talk about a different evolution that's occurred in the broader field. It used to be that we did our experiments on people, monkeys, cats, rabbits, hamsters, rats, mice, lizards, flies, zebrafish. I could go on, right? We had this huge, broad range. And no one said, you guys need to limit yourself to a few model species. But it happened, right? Now, the choice of your experimental subject has become something that people do intelligently. Not because it was enforced on them, but because it became obvious that the major, now I'm at risk of insulting people, the major model organism, the only non-model organism is humans, right? The major model organisms, I think, are monkeys, mice, songbirds, and the conventional, traditional model organisms, zebrafish and Drosophila. Now, yeah, Drosophila, I was coming to that. So it's narrowed down, and the choices are made in very rational ways because the different model organisms provide different advantages for the questions. So I would say that I agree with you that computational modeling has been all over the map, but I wouldn't want to try to legislate who should do what. I would rather like to see people lead by example and see a number of different computational paradigms come to the fore and become accepted and let it evolve naturally rather than imposing it.
Let me also just comment that computational modeling is used for many different sorts of purposes. So I think where the real danger has been is when people try to construct computational models in order to fit some pre-existing data set. And the problem there is, I mean, you can actually prove mathematically that it is possible to model with many different architectures, something like that. But there are frontiers, and there are frontiers that are tremendously active today, wherein computational modeling is not only very exciting, but it's really the only game in town because there's nothing else we can do. So one of my favorite examples of this is the study of evolution. We cannot do experiments in evolution, but we can do computer modeling of evolution. And we have learned, hearkening back to some of the themes we've talked about, that our intuitions about what is likely and not likely to evolve are radically misguided. So my favorite example of all time surely is the development of the eye, where various religiously minded people have often commented on the wonderful complexity of the eye, say, as an example of the sort of thing that it seemed very unlikely or unfathomable how that sort of thing could evolve. Well, today there are testable computational models where you can build in initial assumptions, you can model natural selection, and then you can go to lunch and you can come back and you can see what has evolved. And what we've learned from this kind of research is that, given certain contextual assumptions, that the evolution of such things is quite likely. That these things are actually more likely to evolve than not under certain circumstances. The point being, this is a revolution in science. We had no way to explore such questions before the advent of that sort of modeling. So despite my negative comments about computer science, I am very much a fan of that sort of work.
Good. Do we have a microphone over here?
Sorry, actually, I want to continue on that question just now. Her question about this. Actually, I'm thinking about this about cognitive science, about a bit about philosophical. As Thomas Kuhn says that we always have a scientific paradigms which controls how people think. For example, the heliocentric and egocentric. For now we are all heliocentric people, so we see the evidence everywhere that the Earth is surrounding the Sun. But back in a few hundred years, people think that the Sun is surrounding the Earth. Even we are seeing the same thing. Actually, we interpret the same thing with different paradigms. And so currently, I believe that the most of the models are coming from, more or less influenced, even not directly comes from the computer models. They are more or less influenced by the computer models. So that my question might be a bit radical, is that what if it is not the way, such as Albert Einstein say that we shouldn't think that the things as absolute. We should think as everything is relative. Which everybody think of everything as absolute space and time is completely wrong. And so, is there what can we find out if there's something out of the box, outside the box of the big box of the computer related model, or this kind of issue?
I'm tempted to jump in as a panelist myself here.
I think that would be welcome.
Okay. Computer models have a lot of properties that allow us to do amazing things. I mean, they run. This is not true of a lot of other kinds of models, but in science, models have been used forever, and computer models are just one kind of model. And all models are subject to testing and breaking, or else they're not, worth whatever it is that they're representing. I mean, really. Models break, and in fact that's largely what one of their primary values. And so I don't think this is to say that computer models aren't somehow special and that we can't think outside them. They break also. They make wrong predictions. They are constantly being rewritten. So it's just a very special kind of model that's sitting there implemented in a way on a computer, but they function in much the same way that models have always in science, and that's an important role in helping us establish and ask certain kinds of questions, and also helping us change the questions when they don't work the way we would expect or hope.
Are you asking, though, how we break out of the sort of linear progress that is made by making computer models and finding out where they break? Are you asking about how we get outside of the existing paradigm?
Maybe I should say that is it possible or to develop another kind of paradigm other than the computer-related model?
I would be interested to know what each of the panelists think of as, in answer to this question, as a real seminal breakthrough that changed the paradigm in our lifetimes.
And our colleague Charles Lim will answer that question first.
So I think that the discovery of synaptic plasticity was a paradigm-shifting discovery. The discovery of long-term potentiation by Lomo and Bliss, and in parallel, the discovery of synaptic plasticity and aplesia by, interestingly, a model system that's more or less gone out of style, in aplesia by Eric Kandel and his colleagues. And that changed the way we think about the brain, because it showed us that learning was a physiological phenomenon. Okay, I answered my own question. Does anybody else have an answer?
I don't honestly even know what we're talking about anymore.
Okay. So, thanks.
I tried.
Yes.